Well, welcome to EV Society's Canada Talks Electric Cars. My name's Tim Burrows, and I'm delighted to be able to host this, our 31st regular episode of the webinar. We all know that electric vehicles have an environmental footprint that is much smaller than their combustion-powered ancestors. It's important to note, however, that EVs don't get a totally free pass either. Manufacturing EV batteries requires a cocktail of minerals such as nickel, lithium, cobalt, and manganese, all of which in turn rely on the mining industry. While Canada is well positioned globally to be a major source of these minerals, efforts are needed to ensure that mining takes place with an environmental and sustainable considerations in mind. Today, we'll be learning about one ingenious way some very clever people are using science to recover minerals for EV batteries from mining waste while doing it in a sustainable manner. Helping us later today with your questions is Sean Hart, longtime member and past Vice President of EV Society. As usual, we'll keep a close eye on the clock and we'll end the broadcast no later than 8:30 Eastern Standard Time. Today, we're delighted to welcome Dr. Nadia Mykytczuk, who currently serves as CEO and President of Mirarco. That's an acronym for Mining Innovation, Rehabilitation, and Applied Research Corporation. It's quite a mouthful. And they're based out of Sudbury, Ontario. She also serves in the role of Interim Executive Director of the Goodman School of Mines at Laurentian University. Until recently, Dr. Mykytczuk was an associate professor and industrial research chair in Biomining, Bioremediation, and science communication at Laurentian. Dr. Mykytczuk continues to operate her research lab and supervise graduate students as part of ongoing research efforts to expand biotechnology applications in the mining field. She's currently working on the development of a new center for Mine Waste Biotechnology that will be focused on extracting metals, including battery elements, from mine wastes in a low carbon, environmentally sustainable way. So welcome, Dr. Mykytczuk, to Canada Talks Electric Cars webinar. So glad to have you here.
Thank you very much for having me.
Yeah, well, we met briefly in Sudbury at the Mines for Mobility conference, and you put on a terrific lecture. And so I think folks are really going to enjoy what you have to say tonight.
Thank you very much. And I hope that the discussion doesn't get too technical, but we will cross a bit of a full gamut. We're going to go on a bit of a journey to help explain to the audience here tonight how we can think about mine waste differently and in the lens of feeding that massive demand that we have to build the batteries to drive all the cars that we anticipate to have in just a few years on our roads.
Fabulous. Well, I'll let you have at it. Cheers.
Thank you. Thank you very much. All right. So as Tim mentioned, I'm currently working and CEO and president of Mirarco Mining Innovation. We do a number of different things working in the applied research sector. So just to give you a bit of understanding of the scope of things that we work on, Mirarco has a long history in supporting geomechanics and mine research in deep mining initiatives. How do we extract primary metals and ore from underground? How do we do this safely to ensure that both the operators below ground and above ground are operating within mines safely? Can we build better tools to have those mines operate with software that helps them predict and make mining more efficient? And of course, can we look at integrating mining and minerals into a decarbonized grid and the energy demands that we have? So that is historically what Mirarco has worked on. And with my joining of the corporation just over a year and a half ago, I'm bringing my research field and 17 years of work in biomining and bioremediation. So I understand that those two terms might be new for most of the listeners here, but I assure you that by the end of this talk, you'll have a good understanding of how we use bacteria to tackle something. So tiny microbes, how can we use them to tackle something so large as the massive tonnage of material that we move in the mining industry? So without further ado, We're going to be talking about something that I believe has been discussed probably several times on many of the episodes here on the EV Society. We're looking at a massive transition in decarbonizing our grid, on decarbonizing our vehicles. Everything that we do that currently burns fossil fuels is going to have to transition away to other energy sources. And when we look at that, when we talk about batteries or the vehicles that we build, that is a very broad range of metals and minerals that are needed. And of course, if you don't grow it, you mine it. And this, looking at the spectrum of elements here, a lot of these metals are rare. Many of them, like the rare earth elements, are not located evenly all over the planet. We have to build not only knowledge on how to extract them, ramp up our mining, build the technologies to extract those metals to produce the materials that we need to then build things like batteries, the cars, and of course, the energy grid that is going to support all of that infrastructure. So without question, when we talk about the transition away from fossil fuels, we have to talk about a massive increase in mining. And as Tim mentioned at the beginning in his prologue, you really do have to think about what is the environmental impact of that increase in mining? What is the potential carbon footprint of ramping up all that mining just for us to reduce that carbon footprint from burning fossil fuels? So there's lots of things to think about when we consider the massive increase in mining that we're going to see to meet this demand in battery minerals and electric vehicles. So something I'm sure that you've talked about previously, but we're going to just review together here. When we talk about battery minerals, we're going to focus on a handful here. These are ones that I work on specifically in biomining, so we're going to focus in on them a little bit. What you see in these little bar graphs here, you see what the tonnage we have produced globally right now in 2020 for elements like copper, lithium, nickel, cobalt, and carbon. And then we have what we anticipate in only 8, soon to be 7 years, by 2030, looking at the anticipated demand that we have just for electric vehicles and battery production. That does not include the grid demands, that does not include the other areas that are also going to rely on these elements when they make their transitions. So if we look at that, quickly doing some math there, we're seeing anywhere from 3 to 10 to 14 times increases by the next decade, and that again by 2040. That is an incredible increase in metals that need to be mined. If we look at that on a spectrum historically, we have to mine the same amount of metals in most of these categories that we have mined in the entire history of humanity. So in the space of copper, for example, we have to mine in the next 50 years what we mined in the past 500 years. So there is a real rapid increase that we anticipate, that we need to see. And that, of course, comes with many challenges. When we look at what you see here are bar graphs that are illustrating the known deposits that we have around the world. So in the 4 panels, you have lithium, nickel, copper, and cobalt. And the bar graphs, the colors that you see are the demand that we have is the gray line at the top. And all of the bar graphs are showing us known supply, known deposits, things that we have already mapped, know we can extract, potentially can extract, and maybe possibly if we refine some of the processes and de-risk some of these resources, we might be able to extract them. But what you should all be realizing as you look at this, there is a big gap in these critical minerals between all of those possible sources of metals and what we need to build batteries and electric vehicles. So that presents a massive multi-million ton challenge. And where are we going to find those minerals is a question that not only Canadians are thinking about, but the entire world is thinking about. If you've been following the news, the question of finding that missing supply, how are we going to do and meet this demand, of course, is at the forefront of what we've been talking about in Canada. We know that the federal government has released their Canadian Minerals and Metals Plan. We know that they have a focus there on critical minerals, ramping up production and supplying the many critical minerals that Canada has in all of our natural resources. And provincially as well, I've just highlighted Ontario's plan, since that's where I'm situated, Ontario's critical mineral strategy. Every province is looking to do this as well, since our distribution of these critical minerals, of course, has their intensity in their pockets all across the country. So as we think about where we're going to find this missing supply, we're starting to build the framework. We understand and identify where this missing supply is going to come from. And there's some key areas. So obviously we have to enhance our exploration. We've got to increase the size of those bars that we saw in that bar graph, developing those deposits, building new mines. We have to build hundreds of new mines. That's going to take time. It takes time to explore, do all the feasibility, build a new mine, and bring it to operation. In existing mines, we have to overcome some of the challenges that are associated with going deeper. Really, we are limited by depth as we go deeper. There's greater stress in the rock. There's greater ventilation challenges. There's greater heat pressures. And we also have to innovate how we can safely get our mines and remote vehicles to operate underground to bring ore out of existing mines. At the same time, we can improve our processing, extract more of the metal out of that ore. And those are some key areas that have to be worked on for us to start meeting that demand. But one area, and this is where we're going to spend most of our time talking today, is where else can we be finding that missing supply? And is there a way to start extracting more of those critical minerals sooner? And one of those options is to start looking at what's already sitting at the surface. We have a lot of discussion around the circular economy. What can we do to start tapping into the metals that are already circulating, either through recycling, through existing batteries? But really, those are still going to be quite limited. We actually have to look for raw materials that are right now not being utilized. And so, again, Canada-wide, we've been looking at this question now for a number of years, and Natural Resources Canada has brought a lot of people together to build what is a pan-Canadian strategy for mining value from waste. And when we talk about waste, we're specifically going to focus in on mine waste. And don't worry, if you don't know what mine waste is, I'm going to tell you all about it, and you're going to get more familiar with it. So if we put all of this together, you can see that the cycle, every step along the cycle has the opportunity to help fill in that gap, that missing supply. So all the way from mineral exploration, mineral processing, getting the metals out of the raw materials, producing the batteries that we need, and then ensuring that those minerals are circular and all of that raw material is going to be recycled and back into the supply chain. So you may be thinking, well, this all sounds good. Where can biotechnologies like biomining fit in? And there's two opportunities for us, and I'm going to guide you through both of those. Bioprocessing, and I'll explain how we can use bacteria to help fit in some additional tools to help extract metals that we need, and also aid us in the recycling and reducing the footprint of some of those wastes that we might be leaving in the environment. So let's do some Mine Waste 101. For some of you, the mining industry might be very familiar, but for others, maybe you don't really know the number of steps that we go through to extract a particular element from a raw material, from a rocky substance. So this is very generalized, but I'm doing this in order to illustrate where we generate mine waste and then talk about what those mine waste entail. So when we're mining the raw material, the ore, typically a rocky substance, either extracted deep from underground or mined from the surface, is usually a small component of the rock mass. So a small percentage of what we're going after is contained within a rock mass. We have to, mine that. We have to break down what is known as comminution, so crushing and grinding and breaking those large rocky materials down into smaller particles. Once we have them in smaller particles, we typically have to concentrate the material. We want to use processes like froth flotation that you can see here in this little image, and that'll help separate out some of the minerals that we're after from the gangue material, or what we call the less valuable material that will also be discarded. Then we typically have to process that concentrate either through chemical processing or heat processing, like building smelters. And then we convert and refine that metal material to produce the final metal product. So every step along this pathway, you have different energy inputs, different carbon and water footprints, and different wastes, solid, liquid, and gaseous wastes are produced. So that's a lot of different wastes that we could be talking about, but we're really going to focus in today on solid mine waste and why these could be a particular source of metals that historically we've ignored and thought they're not worth it, they're a waste, we're going to leave them aside. So let's focus in on this colorful pile of rocks here, and we're going to take an example of sulfide minerals, nickel, copper sulfides. Those happen to be the ones that we mine here in Sudbury, where I'm located. And you can see that the nickel, the little green chunk or the little purple chunk that you see in those rocks, is actually a very small percentage of the rock that we're extracting out of the ground. And a lot of that has a lot of sulfur. Now we have to, we typically extract and remove and separate out that sulfur. Historically, we used to burn off all of that sulfur, and that created a big sulfur dioxide problem. That's a subject of another story, but we have to be conscious of all of these transformations and all of these elements that we separate out when we're targeting elements like nickel or copper. So when you're looking at all of this rock and you're thinking, well, we really are only after 1% or less of that rock material, that gives you a sense of scale. So for every 100 to 1,000 tons of rock that we extract from underground, we're only producing about 1 ton of metal. That is a staggering volume issue. So if you think about it, mining is really a waste management industry and process because it produces a lot more waste than the target element that it is actually capturing. So you're probably thinking, my gosh, I didn't know what I thought about the mining industry before. And now I have a lot of concern because this seems like a real challenge. But let's start to look at that challenge a little bit differently. The difference between ore and waste is the cost of extracting the value that remains in that material. So historically, if we were to take those rocks, crush them up, use a lot of energy to get at them, put them in smelters to get at, this nickel bar that you see here, there's a lot of value in that metal. And the waste that we have left over from that process, because no process is perfect, still contains a small amount of elements. We typically thought, okay, it's not gonna be worth it to take that material and run it through the process again, or throw it through another process because the cost of doing that versus the value of the metal isn't going to be high enough. And so we have developed an industry that generates waste that are very low grade. They're not considered ore. They're considered a waste because the material is very low in concentration for these target elements. Now, that presents a large issue. If you think about it, the wastes, which are very high in volume, right? We produce all of these extra tons of waste material for the small amount of metal we get out of it. They can potentially leach into the environment and cause long-term potential impacts. And so the mining industry really has to manage these wastes very carefully to make sure that that impact isn't severe. So again, what can we do about this massive challenge? Well, let's start to look at mine waste a little bit differently. Here we're looking at a Google map of something that's just in my backyard. This is the footprint of a mining operation here in Sudbury. And what we've highlighted for you on the map, there's waste rock piles, there's materials called tailings, which are the fine mill residues that are typically deposited in ponds. There's seepages, so liquid waste, smelter emissions, and other solid waste like slag. What if we started to look at these materials less as a problem, but more as an opportunity? So bear with me for a second. You might think, how can this low-grade material have anything to do with the demands that we're seeing right now? So let's go out onto one of these tailings ponds. This is an old tailing site. It looks like a fine sandy beach, but in fact, these materials still have residual metal. They also have other elements that can cause impacts to the environment. And typically what we've done is we've managed these sites, we collect the seepage from these sites, we treat it to reduce the impact to the environment. But these materials don't go away on their own. We accumulate them at the surface all over Canada. And here's some numbers just to give you a bit of a sense when we talk about mine waste, how much we're talking about. So Canada has about 200 active mines. We have about 10,000 to 15,000 abandoned mines. Many of those have deposits of solid mine wastes. Annually, operating mines are generating about 650 million tons of tailings material, so this fine sandy material. And of those, many of those, of course, are considered potentially hazardous and have to be maintained. And that presents a large liability for mining companies. They have to spend a lot of money to ensure that those wastes are contained and not having any additional impacts. And that is on the order of billions of dollars. So not only is there value sitting in these wastes, we're also spending a lot of money to ensure that they are not having a downstream impact. So here's the switch that I want you to do in your mind. Tailings are these large volume wastes that are produced as a byproduct of mineral processing. They're seen as a liability, they're a problem. They're low grade, they potentially leach out into the environment. It's not worth it putting it through a smelter again because the amount of material we'd get out is very low. And yet, if we see this as an opportunity to find better ways of extracting those residual elements, we can tap into something that is pretty incredible. So if we look at the tailings contained in that Google image that I just showed you a few slides back, the nickel contained in the Sudbury region, if we were to able to extract it out of those tailings materials, is on the order of 8 to 10 billion worth of nickel. We look at a similar, it's not a critical metal that is used in battery production, but you can see an estimate here for gold. And globally, if we look at copper, which we know is a critical mineral, 2.4 trillion is contained within these mine wastes. So if you look at that for a moment, we know that there's that massive gap in the demand and all the potential sources of ore that we know underground. We have a lot of metals sitting at the surface contained within these mine wastes. So how can we start tapping into that in an economic and environmentally sustainable way? This is where we enter the microbes. So can we find alternative strategies that can extract metals, lower cost, lower footprint, and more environmentally sustainable way? So there's a little video that's going to play here on this slide. We're zooming into inside the rock, and you're going to start thinking about microscopic cells, these bacteria that are able to break apart the mineral. So in this case, they were eating sulfide minerals. In that process, they're breaking apart the minerals. Here, we'll show you that little video again. Here we go, just so you can see it happen. Just like we eat food, these bacteria are breaking down those minerals, and in the process, they release the metals into solution. If we concentrate that solution, we can actually extract the metals from those residual wastes. And when we look at that in comparison to putting that material back into a smelter, which would be too costly. We're actually recovering more of the mineral that is left in those wastes for sale. And at the same time, we can render those wastes, those tailings, less reactive because we're extracting some of those metals that were there and problematic. And we can also deal with some of the other elements in those wastes that could have downstream environmental impacts. So let's look at this a little more closely. So bacteria, these are naturally occurring bacteria. They've evolved over time, just like the bacteria that evolved to live in our gut, or environmental bacteria that naturally grow in the environment. These bacteria have evolved to eat elements like iron and sulfur. This is how they gain their metabolic energy. And we can use them like little biological catalysts. So they're little engines that we can use, little smelters that we can use to break apart those minerals and extract the metals. What we get out of it at the end, if we're talking about these iron sulfur bacteria, is that we're releasing and separating out all of these elements. The iron and the sulfur typically come from sulfide minerals that can contain nickel, copper, cobalt, gold, and then those elements we can extract and use to make battery minerals. So you might be thinking, well, this sounds like brand new idea that can't possibly be anywhere near commercial application. You may be surprised to know that biomining or bioleaching technologies have been used for over 40 years. We have several examples around the world where bioleaching is used in a method called heap leaching. So the image you see here is ore. So this is not waste, this is ore stacked on piles or heaps. And this is a heap leaching pad in Quebrada Blanca mine in Chile, where they're extracting copper. So these piles, you can irrigate them with dilute acid and these iron sulfur bacteria. They leach through the pile, their metabolic activity breaks down those minerals. And what you get leaching out at the bottom of the heap is then this concentrated slurry that contains the metals that we're targeting. That concentrate can then be taken to different types of chemical processing to produce either primary minerals, or if we think for the battery supply chain, producing battery feedstock. For slightly different applications, heap leaching isn't always well suited. In a climate like Canada's climate, where we have a lot of seasonality, heap leaching might suffer from that range of temperatures, the range of precipitation. So we can also build these bioreactors, which are concentrated environments that contain the material and keep the conditions stable. Same idea though, you put in the ore or the mine waste material, you add a slurry of bacteria, and usually it's acidic, and the bacteria will work their magic, break down those minerals, and what you get out at the end is a material that can be used for battery production. So biomining, in fact, is not limited to just one type of rock or one type of mineral. We can actually use different types of bacteria to extract elements like gold, copper, uranium. Those are the most common that we've seen globally, and some examples of those are on the side. But we're now, because of this battery metal demand, thinking about targeting different types of materials that we really haven't looked at in the past, primarily because they're lower value elements, and there just hasn't been that push or that demand to go after all of those waste materials. And when I'm particularly highlighting cobalt and nickel, as we know, those are primary elements that we have in EV batteries. But other elements like zinc, lithium, and rare earth elements, of course, are important to not only battery production, but the electric grid. So why hasn't biomining become a dominant technology? There are a lot of challenges. It's been a niche technology for 40 years. If you think about the mining sector, we learned how to build smelters, we learned how to do various types of processing. There really didn't seem to be a need to bring in a lower efficiency, but better cost process like biomining. So we have industry confidence in known technologies, pyrometallurgy, hydrometallurgy, and that industry demand and investment really hasn't been there for biomining technology. It is true, biomining does have a few caveats and challenges. Bacteria don't work as fast as a smelter does. There's longer processing time compared to conventional processing, days to months, compared to hours. But if we're targeting a waste material, that time frame, time is money, is less of a challenge. Biomining can still suffer from reliability, and this is part of the reason that the industry really hasn't seen biomining as a reliable technology, and that biology can be a bit tricky, and controlling that black box of bacteria historically has been a bit challenging, but I'll show you how we're refining that in just a minute. And proven biomining applications have been limited to a handful of minerals. We've targeted, as I showed you, there was gold, copper, and uranium really were sort of the high value or high risk elements that we used with biomining. But all of that is changing now. So I'm going to address some of these issues that we're now working on to help bring biomining to a reliable, commercially applicable tool to help us meet this challenge. So here's my preamble for this slide. This is my most technical slide, and I'm not going to go into too much detail, but I want to just show you what this level of innovation and what the science looks like when we talk about developing biomining technologies. So this is an example for the Sudbury materials that I was talking about and showing you earlier. We have a mineral, pyrrhotite, that was rejected from the smelter from the mill in the tailings for many decades. And there is a concentration of nickel and cobalt retained in those tailings. You can see the concentrations here. And what we're working on now with our collaborative network is looking at different biomining processes. We've got one from our colleagues at the University of Toronto that was developed under the Elements of Biomining program. We've got one developed by CanMet at Natural Resources Canada, and a process being developed by a biomining company called Backtech Environmental. And so what we're looking at is how do we develop the best process? What's going to be most efficient? Which bacteria are most reliable? Can we build and engineer the system to be feasible, and that we get the right products at the end of it? So the goal of the project, one of the projects that we're working on right now, is to pilot, so scale up these processes, ensure that the process works well. Can we extract cobalt and nickel battery mineral salts? And the TEA stands for techno-economic assessment. Can we show that that is a viable, economical solution? So the bacteria piece, how do we deal with the challenges of controlling biology? Well, you may have heard of genomics tools. These are tools that we can sequence DNA from any environment. And so when we look at the diverse community of bacteria in a pile, really, we only want to hone in and target a handful of bacteria that are doing the types of activities that we want them to do, breaking down those minerals. And so now we can use DNA, we can sequence that and use genomics tools to help us control, predict, and make that microbial black box more reliable. We can ensure that the process, just like any other thing you're measuring, right? Temperature, pH, all of those things need to be controlled in a commercial system. Same goes for the biology, and those bacteria need to work for us, and we need to make sure that they are happy and doing what they do best. So as we develop these technologies, we know that we have to scale them up, and we've got bench scale, slightly larger. This is typically research that's done at a university. We have to pilot it, and ultimately we have to demonstrate that technology so that it works at commercial scale and can compete with standard processes like smelters and hydromet processing. So There's another advantage that we have to think about. There's a green advantage to biomining. When we talk about battery minerals and producing battery minerals, we don't want to have a massive carbon footprint. We don't want to have a massive environmental footprint from simply producing elements that are going to shift us away from fossil fuels. So here we have just a simple table to compare the advantages of biomining compared to traditional pyromet processing. So you have all those steps in mineral processing that I briefly described early on. And you can see that for pyromet or smelter processing, you have a very high cost, high carbon footprint, and that gets reduced when you use heap leaching or bioreactors. Here, what you should see, hopefully, is the big switch from when we're looking at biomining of ore versus biomining of tailings, so reusing those mine wastes. We reduce the cost and the carbon footprint of extracting those metals, primarily because they're already ground up, they're already sitting at the surface. And so that the total operation of getting those elements out of those materials is a much lower capital cost, operational cost, and a lower carbon footprint throughout. So how are we, my team, working on scaling this up and accelerating these biotechnologies that are needed right now to help address the gap in EV metal demand? So we've done a lot of the legwork. We've got a lot of people working on at the academic level, at the government research level, to prove up these technologies and have a process that works. We then have to get through these, I forget what we call it, the TRL level, that right in the middle. That is where many technologies sometimes falter and don't really get through this gap. You have to scale up, de-risk that technology to show that it is commercially viable. And we have to make sure that we can get it scaled up in order for the industry to adopt those technologies. So we recognize this gap, and we're proposing to build a Center for Mine Waste Biotechnology that does exactly that, scales up and de-risks biomining, bioleaching, bioremediation technologies that can be used, and specifically targeting this massive inventory of mine waste that we have in Canada and in many other locations around the world. So we've been just completing the feasibility and business case for this center, and I'm going to show you a little bit about what we intend to do to help fill this gap and accelerate this process. So we recognize that there's a need to specifically focus on EV batteries and battery minerals. This is where the biggest demand is going to come in the next 15, 20 years. We know that in order to scale up and prove up technologies, you have to move very quickly through these TRL levels and pilot these technologies to show that they work. And we have to connect and coordinate not only with research, but the private sector and ultimately the technology end users. The vision for this center is to not be a silo. We really want to have the researchers talk to the private sector, work with them to help commercialize these technologies. And we can really only do that collaboratively. We now see a lot of the battery mineral supply chain. We see automotive companies talking to mining companies, talking to technology companies. In order to do that rapid acceleration, we really have to connect the dots, and we want to help be part of that in targeting these particular materials and help supplying the battery supply chain. The goals of that center are not just to prove up the technology, but we really want to foster that market confidence in biotechnologies. Mining really hasn't used biotechnologies historically, and we have to de-risk and create opportunities for integrating this new tool as part of all of those innovations that are happening across the supply chain. And there's an opportunity here. We can tackle materials that have been sitting in some of our landscapes for up to 100 years and extract metals and help reduce that environmental footprint all at the same time. Some of the facilities, as you can imagine, this type of process development has lots of different disciplines. So we have chemistry, biology, mineralogy, all of these people working together to help make sure that we have a reliable process for any mining waste material that we target. So the next steps that we are working to fundraise and develop the center. I'm hoping to be breaking ground on it by the end of the year next year. We know that the rapid increase in battery metal demands is going to, push the need for new innovations. And we really want to be there with a good suite of technologies that can be used for mine waste that are ready to be reprocessed. Ultimately, we want to address the environmental footprint at the same time as we're creating value. So moving away from large stockpiles of mine waste, reducing the footprint of those materials and helping extract the metals that are there, and improving the mining impact on the environment. So combining all of that together, hopefully you can see that mine wastes aren't technically a waste. It's how we think of them. They're actually a resource. We have the tools and we are developing and scaling up those tools to use biotechnology to get at that metal value. And we want to commercialize these tools because they're actually a very important strategy as we think about green critical mineral supply, ensuring that there is a lower carbon footprint and better environmental footprint for the battery metals that we are producing. When we think about that whole supply chain, of course, there's challenges all around that supply chain, all the way from primary ore and mineral development, exploration, developing the mines, recycling the metals and the batteries at the end of life. But what we're trying to do, and hopefully you appreciate that now, that there's other tools that we have and there's other sources for these metals that we can start tapping into. And bacteria are part of that solution. And biotechnologies can be a viable method in the mineral resource industry, and particularly the battery mineral industry. So Canada in particular, I think, is very well positioned to support accelerated development and commercialization of biotechnologies for EV battery metal demand. We do have a strong mining sector. We have so many of the critical minerals both below and above the ground. Hopefully now you appreciate just how large that inventory is of material and mine waste sitting above the ground. We as Canadians, we have committed to both lower carbon footprints, so greenhouse gas reduction, and ESG, environmental social governance, as part of our mineral resource plan. And so that gives Canada a really large edge, that if we maintain these commitments in what we do and how we produce our battery minerals, that we can actually put that green stamp on them. And that will be highly sought after compared to other mineral resource sectors globally. And so we really have to come together and work to connect those dots across the supply chain in order to ensure that we're using the best technologies. Biomining is just one tool in the toolbox, and we have to see how that fits in and how that works across that whole supply chain. So the punchline is we really have to think about those mine waste differently, and we have the opportunity to use them to ensure that our carbon transition is as green as possible. So with that, I'd like to thank the EV Society for inviting me this evening, and for everyone that's on here who has listened. Hopefully you went along for the journey and you learned a few things, and I'm very much looking forward to all of your questions. Thank you.
Just absolutely terrific. Thank you, Nadia. That was so well explained for me as a non-science guy. That was really helpful. I'm sure it was enlightening for the folks watching. So I'm not going to take up a lot of time here. We want to get to some questions. I didn't mention it earlier, but if you do have a question, please put it in the appropriate box there, the Q&A. And if you see a question there you want to hear answered before we run out of time, give it a thumbs up. It'll move it to the top of the list. So with that, I'm going to introduce Sean. Sean, I'll let you go at those questions.
Great, thanks. Thanks, Tim. Thanks, Dr. Mykytczuk. So we've got a number of questions that have come in. So I'm going to start taking them in order of the thumbs up here. The first one is from Steve, and he asks, what's your best estimate for for the timeline for commercial viability for what you've talked about?
So for nickel and cobalt in particular, and copper as well, there are several processes, biomining processes, that have already been going through a lot of proof of concept and trialing at those mid TRL levels. So we have sort of the best horses in the game as we work to scale up and de-risk. So I would say within 3 to 5 years, we have a commercially viable process for pyrrhotite, for nickel and cobalt extraction from those materials. For every mineral type, for every waste type, we likely have to optimize and tweak that process, and then scale that up. But I think once we have a recipe for a particular type of mineral, we can apply that to different mine waste at different operations. So we're trying to keep that timeline, I'd say within 5 years for each of these processes that we're talking about.
Okay, great, thanks. The next question is from Bill, and he's asking about the trend to eliminate cobalt from some of the battery chemistries, and if that kind of impacts, what you're looking at all.
Yeah, so there are challenges, of course, with different elements and where we have historically sourced them from. Whether that is a mineral limitation challenge, whether that is an ESG challenge. There is a lot of reasons for market demand and hesitancy around certain elements. The reality is that we're actually going to need a diverse set of battery chemistries, because we simply won't be able to have a single battery chemistry, because we simply won't have enough of the element to build an exclusive one battery fits all. So nickel, cobalt, lithium batteries, and some of the new chemistries that are coming out are all going to have a chance, I think, to be commercially viable and in high demand, because we simply have so many cars and so much electrification to do.
Okay, great, thanks. The next question is from Glenn. He's asking about he says first, this is very encouraging, and he's asking about the tar sands in Alberta and if there's any potential for biomining there. Yeah,
so the tar sands come with lots of different challenges. The hydrocarbon residues sort of foster a very different community of bacteria, and we have to sort of pre-process those materials, separate out those hydrocarbons when we target some of the other elements. The tar sands are an incredible source of rare earth elements in particular, and I think as we mature these types of technologies and get better at mining value from waste, we're going to have to consider some of these really large, environmentally risky deposits like the tar sand tailings to start going after the residues that have a lot of impact, clean them up, and extract the value that's there. Overall, I'd say from my perspective, I don't work in the tar sands materials, but there is good research being done there to valorize or get the value out of those materials. But it is a little bit trickier because of that hydrocarbon piece.
Thanks. The next question is from Andrew, and he's asking what's being done or what needs to be done to ensure the bacteria that you're working with isn't released into the environment. Is that a concern? And
it's a great question. Yeah, no, it's a great question. I think a lot of people, when we hear about bacteria, we think, oh gosh, what's going to happen if we release them into the environment? So the beautiful thing about a lot of these bacteria is that they've evolved over billions of years. These are naturally occurring bacteria, and they've found a niche that they can survive in. So for example, the ones that I talked about today that extract nickel and cobalt from pyrrhotite, they live in very acidic conditions, and they really can only eat iron and sulfur. And when you throw in a bit of carbon or you change the pH, they die out. They have natural limits. And so when we talk about them in these processes, they're contained either within the heap or within the bioreactor. Once we process those materials and we're neutralizing any of the acidity or anything else that comes out of those processes, those bacteria are dying out. And so there isn't really much risk associated with them. None of them are pathogens. Humans are carbon-based. We are not a food source for them. And so there isn't really a lot of concern, although of course, anytime you have any process, you would contain the bacteria as you would any of the other liquids or materials that are going through that process. So you really wouldn't be releasing anything into the environment before neutralizing it.
Okay, great. Thanks. Next question is from Bernadette. She's just asking, is there currently any biomining happening in Vail, specifically in Sudbury?
Yeah, and Vale is a strong supporter, obviously, of this research, and I work very closely with them as they are the inventory holder, one of the inventory holders for the materials that we're working on. But right now, at a commercial scale, no, there isn't any biomining being used at Vale operations. There is a handful of trials being done at different mines across Canada, but there isn't any full-scale biomining operation yet in Canada.
Okay, great. Thanks. The next is from Leslie. I understand there's an assessments being done to evaluate if there's enough cobalt to be recovered in the waste of the old silver mines in Cobalt, Ontario. Do you know where that's at?
So Cobalt, Ontario is it really is an amazing place with a really rich history. You know, you think people used to travel to Cobalt, they'd go through Toronto just to get the train to go to Cobalt. It really was, you know, during the gold rush days, such a vibrant early mining town in Canada's history. And with early mining comes really poor processing. And so there's a lot of material and waste in Cobalt, Ontario. And there are a number of companies that have looked at reprocessing. There's battery production plants that are going to be built nearby. So I think many historic towns like Cobalt are actually well positioned and poised to be, you know, hotspots for battery metal production, because again, these wastes are well suited to this type of lower cost, lower footprint reprocessing. And so I have a lot of hopes for a lot of activity up in Cobalt.
Okay, great. Thanks. Volker's asking, how open are Canadian mining companies to these processes and investing in these processes?
Yeah, so that conversation has really changed in the last couple of years. So when I started my career, the discussion of biomining technologies was really from the environmental lens. Like, we were really trying to apply these technologies just to help clean up the sites. There was less interest from the mining companies to say, oh, you know, can we extract some of that metal value? They were very much focused on the ore, primary materials underground, higher value, more bang for your buck. Now, when we look at, again, that gap in supply and demand, many mining companies all across Canada, globally, are all starting to think, let's look at our entire inventory, wastes included. Can we start extracting some of those metals? Is it worth it? Are we, you know, going to create a bigger challenge for ourselves, reprocessing waste materials? But overall, that whole conversation has shifted to an openness to say, okay, what are all the processes and technologies that are on the table that we can use to help address this demand? And so it's actually a very exciting time to be in my particular field, in the mining industry as a whole. We're going to see you know, an incredible boom in the mineral resource sector globally as we decarbonize. So it is a lot is happening, and there's a lot of interest and support from industry.
Great. A couple of folks have asked about funding. Do you have the funding you need to do your work? And can you talk about that?
Yeah. Generally speaking, first, funding is a challenge for research in Canada. I think if anybody was listening to Minister Champagne recently, our innovation minister at the federal level, saying, you know, Canada hasn't really kept up the pace with funding primary and applied research in Canada compared to Europe, compared to the US. So it's hard. It is hard to get research dollars. It is hard to get enough investment to carry things from those early TRL levels all the way up through and to something commercial. So what we're seeing now is a lot of partnership, having private sector investment matched with government funding, helping build out that pot of money needed to work on these technologies and scale them up.
Okay, great. Next, we've got Barry's asking, and I think you touched on this a little bit, but where are the bacteria found and how fast do they reproduce?
That's also a great question. So when I say bacteria, I'm actually talking about thousands of different species. So if I had a little, pocket of mine waste in my hand right now, there'd be 100 million different bacteria in every gram of waste. So we're talking about a huge diversity of bacteria. All of these are naturally occurring. Every single bacteria has different types of things they'd like to eat, growth rates under different conditions. Every bacteria likes, their little niche, the certain temperature they like, the pH they like. And so when we create a process and optimize a process, like let's say in a bioreactor, we might have, 50, 100, maybe even up to 1,000 species that are really active under those conditions. We want to get them growing as fast as possible. So in the environment, they might grow more slowly. We want to find the perfect conditions, like a Goldilocks zone, for them to be happy. They have the right temperature, the right food, and they're able to break down those minerals as fast as possible. So that's what we do when we talk about optimizing this process. We're really trying to get those bacteria to be happy and working for us efficiently and effectively.
Hey, Sean, can we squeeze in one more really quick one? We're running out the clock.
Sure, yeah. I just wanted to mention there was one comment that this is very encouraging, that biomining can clean up some of this mess, and I know, personally I've seen this as well, as there's always a lot of questions around mining and EVs, so this is kind of a good news story that we can tell in relation to that. I guess so there's a lot of questions, but I guess the last one I'll ask here is from Keith, and he's asking, just I guess it's more clarifying. So this is what you're talking about is uneconomical as a primary extraction technique, and is that because the ore needs to be ground into a fine powder?
Yeah, so if you look at biomining as a tool to extract ore, higher grade materials, you get better bang for your buck if you process them quickly, higher tonnage, higher throughput. So it makes sense to do that with a smelter or hydromet processing. But there are examples like the mine I showed you in Chile, where that heap leaching operation is primary ore, and that copper is being extracted through bioleaching. So it is possible, but as we look at, how are we going to tackle these lower grade materials, biomining and lower CapEx, OpEx operational cost tools are going to win out, because you wouldn't put this material back through a smelter.
All right. That's great. Well, thanks so much, Dr. Mykytczuk, for showing us how microbiology is helping to increase the output of mining in Canada and clean up the fields. It's absolutely fantastic. Anyone who can take bacteria and make it fascinating is a skilled person, I must say. It's really very interesting. And thanks, Sean, also. Did a great job with the Q&A. We really appreciate that. I always have to remember to thank all the folks who work on this webinar. Big shout out to Chris Guernsey and Anise Sharifi and Jason, who couldn't be with us tonight, and of course, James McCallum. It couldn't happen without all of you. So, Doctor, it was just fabulous. Thank you so much.
Well, thank you so much for having me. And I'm sorry we couldn't get to all the questions. I'm happy to talk about this for hours, but hopefully we get another opportunity some other time. And I'm glad that it piqued the interest for everyone here.
Well, I was going to say, be careful what you ask for, because we may have to get you back for chapter 2. We've done it before. So
Excellent.
Thank
Be
you.
happy to be back.
Great. So in our January episode, then starting off the new year, Canada Talks Electric Cars, we'll be addressing a topic that's not often talked about, specifically how fire and ambulance professionals require new training in order to safely and effectively respond to accidents involving electric vehicles. The episode, entitled First Responders in an Age of Electric Vehicles, features Mike Wakeham, a first responder and a rescue trainer with extensive EV experience, who is employed by the Strathroy Caradoc Fire Department. So be sure to mark the date. It's going to be on Tuesday, January 3rd at 7:30 p.m. Eastern Standard Time. Thank you all for joining us on today's episode. We're fortunate to have such a great group of EV enthusiasts following our EV series. I always wanted to say this, please visit our YouTube EV playlist of past episodes, and remember to like and subscribe, because this really does actually help us spread the word about EVs and electric mobility. So from all of us at Electric Vehicle Society, and until next time, stay well. This concludes today's webinar.